Hi guys, welcome back to my channel. In the previous video we discussed about YoloV4 on a high level. This is part 2 of YoloV4. We talked about why YoloV4 is widely used and different components of YoloV4 like the backbone, what is the backbone used, what is the neck part used, and what is the head being used. And also discussed about bag of freebies and bag of specials. All these we have discussed on a very high level. What are these individual components and what is its purpose. Now in this video, we will dig deeper into each and every component one by one. We will start from the architecture side and then we will move on to bag of freebies and bag of specials. So in this video, we will cover mainly about the architecture and the design choices of YoloV4. What is the backbone that is used and what is the neck part that is used along with some additional modules. We will understand the design choices. Backbone is an important part of object detector. It decides the accuracy because it extracts good features which are used later for detection heads, right? So if you want to improve the accuracy, we have to design a deeper network to have good receptive field. And once network becomes deeper, it becomes complex and it's difficult to train. In YoloV4, CSP DarkNet is the backbone that is used. Now for learning about CSP DarkNet, we need to understand DenseNet, we need to understand CSPNet. So we will go through one by one. We will see why they chose CSP DarkNet53. So if you even see the table here, CSP DarkNet53, it is having good number of parameters like 27 million parameters, but the FPS is 66 FPS. So it is very good FPS. If you compare with ResNext 50 or EfficientNet, right? ResNext 50 has 20 million parameters, but the FPS is 62. And Efficient B3, it has 12 million parameters, but it has 26 FPS. Even though CSP DarkNet is a bigger network because it has more number of parameters, the FPS is high. That is one of the reason CSP DarkNet is chosen. So let us go in detail about the backbone part. CSP DarkNet uses dense blocks and CSP blocks. So we will understand one by one. First we will see what is a dense block. So this is a dense block. You might have heard about the ResNet. ResNet has these kind of residual connections or skip connections, but it is only in between one or two layers directly bypassing. Whereas if you see this dense block, the same idea extended to multiple layers. If you check here, observe this network carefully. Every layer in the DenseNet is connected to all the other layers. So it is like a fully connected network. Every neuron in one particular layer connects to all the other neurons in the remaining layers. The same way here, this is layer number 1, this is layer number 2, this is layer number 3, this is layer number 4. Let's suppose that. Now layer number 1 is going as input to L2 here, and then via this L3 it is going, and then it is going to L4. At the same time, this particular layer is going as input to all the other layers, all the next layers. So it means that each block output is passed to all the consecutive layers. That is what it means in simple terms. Or you can say each block takes inputs from all the blocks before it. If you take this particular block, it takes inputs from all the three of them. This is how dense block looks like. Hope you understand this. You can see an example here even in the form of equations. So if you check, this is my x0, x1, x2 and x3. Now x1 is taking only x0 as the input, but x2 is taking x0 as well as x1 both as the input. You can see here. A DenseNet is the combination of all these dense blocks. So DenseNet can be formed by combining multiple dense blocks, and each dense block has a transition layer in between. You can see this is one dense block and then another dense block. These two are connected by one transition layer in between. The same way this and this are connected by one transition layer. This and this are connected by one transition layer. This is how the DenseNet looks like. These transition layers or even the convolution layers, you can see these are actually batch normalization, ReLU and convolution layer. The combination of these. At the same time, transition layer also, it is a combination of convolution and pooling layer. You can see it is a pooling 2 by 2 layer, batch normalization followed by ReLU, 1 by 1 convolution, dropout and then pooling layer. So these are the definitions of this block. Okay, each DenseNet is having these layers. Each transition layer is having these blocks. Hope you understood the DenseNet. It's very simple. There is nothing difficult about this. DenseNet is formed by dense blocks. Okay, number of dense blocks, and each dense block is just an interconnection of all the feature levels for different layers. you can decide for each dense block how many blocks you need to have. So this 6, 12, 24, 16, all these are actually number of blocks you have. If you check this number here, you have 4. Similarly, you can have 6, 12, 24. How many ever you are having, the interconnections will be there between all of them. Okay, that is what the dense block looks like. And each dense block is connected via a transition layer. So transition layer is only for scaling down. Mostly the purpose is mainly for scaling down. You can see the pooling layer, which is scaling down the spatial features. So this is what dense block is. It's very simple. Now the disadvantage is because of this interconnected nature, right? So there are a lot of computations which are happening. What is the input going here? Let's suppose you have only 4 channels here or 5 channels. So you have only 5 channel input going to input here. For the next one here, you are already getting 4 channels from this path and another 5 from here. So total 9 channels here as input. At the same time, for this particular block, there is another 5 here coming from this, and again from the second block you will get 4, and the first one you will get 5. So this is having 14 as the input. So this keeps increasing as more number of blocks are following like this, because everything goes as input to all the consecutive things. So this kind of complexity will increase. At the same time, when you are doing the back propagation, you usually have mostly like duplicate gradients happening. Because of this interconnection, the gradient which you are passing here from this particular layer, the same thing proportion you will get from this layer and this layer, like this, all these interconnections. So there is an overlapping information happening even during the forward pass. At the same time, during backward pass also, the gradients will have overlapping information. So it's an unnecessary computation we are doing here. There is a lot of overlapping and you can say redundant information it is being used. Now let us see what is cross-stage partial network. Let's suppose that this is my computational block. Okay, this is having some CNN or convolution layer. Now my input I am passing here. Let's suppose that input I am passing 10 channels. Okay. Out of which what I will do is I will split into, let's say, 5, 5. So it is having 5 channels here and it is having 5 channels here. Now only 5 channels are going as input to this computational block and coming over here. Now this particular 5 channels are finally added here. So you can say concatenate. So this is the cross-stage partial network. So you can see that only half the input is passed through the actual computation. The other half is directly passed to the output for concatenation. Okay, this is what cross-stage partial network in simple terms. Now instead of this computation block, you replace with dense block. Whatever we have seen here, now for this dense block, instead of going all the features from here, you take only half of it, and then the other half you directly pass it to this one, transition layer. Okay, let us see this in detail. You can see this is your basic dense block. Starting layer, then you are passing some information, then you are having the dense blocks, and then you are having a transition layer. For each dense block, you have one transition layer, right? Now, your base layer, suppose here, I am saying 10 channels. All these 10 channels are passing through the dense block. Now here in cross stage CSP DenseNet, you have 10 channels here, but you have divided into 2 parts, one with 5 channels, another with 5 channels. Now this only half the information is passed through the whole dense block. You have already seen that dense block is actually a combination of multiple convolution layers which are all interconnected to each other, right? So this only half the information is passed through the dense block. The remaining half is actually passed through a transition layer here. So there is one transition layer for this particular input, and then that output is passed through the second transition layer. And this CSPNet, it's not only for dense block, okay? You can apply for ResNet. Let's suppose you have ResNet where you have parallel connections or like that, right? So there also you can actually pass only half the part. Even you can apply for normal VGG network also. Any computation you are passing through, any computation block you are going through, you just divide your input into two halves, and then pass only one of them through that computation block. The other one you add it directly at the end. So that's what you can apply to any type of network. If you apply CSPNet to DenseNet, then it is actually CSP DenseNet. Let us see in more detail. Okay, this is what actually normal basic DenseNet looks like. You have an input image H, W and 3. Now you have a base layer, then dense block you are having, transition block you are having, and finally you will do concatenation or something. Now in the CSPNet, you actually divide into 2 halves. Okay, this particular F here, it is divided into F1 and F2, and then only F1 is passed through this particular dense block as well as transition block, whereas F2 is directly concatenated here at the end of this and then passed to another additional transition block. Okay, so this is how the CSP DarkNet looks like. CSP DenseNet, sorry. In the YOLO paper, YOLO version 3, if you see, it has used DarkNet53. Now the DarkNet53 has dense blocks. Now all those blocks are replaced by CSP DenseNet, CSP blocks. So finally, this is how the CSP DarkNet53 looks like. This is the DarkNet53. This is used in YOLO version 3. Now you can see these are all the dense blocks. All these are replaced by CSP dense block. And there is one more difference from the architecture in the backbone. In DarkNet53, the activation functions are leaky ReLU. You can check that these are all leaky ReLU activation functions. So all these activation functions are leaky ReLU activation functions. Whereas here, all these are actually Mish activation functions. Okay. So instead of leaky ReLU, Mish is used. So you can see that leaky ReLU is replaced with Mish. Okay. So these are the two major changes applied on top of DarkNet53 to adapt to CSP DarkNet53 for YoloV4. So this is all about the backbone part. We have seen the design of backbone. We will go to the neck part. Neck is kind of feature aggregator. So people call it as feature aggregator. Okay, because neck is actually used to aggregate or collect the information from different levels of feature maps coming from the backbone. Usually the backbone produces the feature maps, right? You can take the output of the backbone at different levels to have different set of features, and you can combine them in a best way to provide better features for the detection, actually predictions. So that is what it is, actually feature aggregator. It is optional. Actually neck was not used earlier in older networks, but it has become the default component in the latest object detectors. And the most common type of neck is FPN, feature pyramid network. This is the most common type of neck which is used in all the object detection networks. In YoloV4, FPN is not used, but path aggregation network is used. It is an extension of FPN. So we need to understand FPN to understand path aggregation network, PAN. And spatial pyramid pooling is also used in YoloV4 in the neck part. So we need to go through these three components to understand the neck of YoloV4. Let us start with the issue. Why do we need neck? Okay. So there is an issue with small objects detection, or you can say especially for bounding box predictions, to accurately predict the offset or the coordinate values, the location of the bounding box, you need good spatial information. And you know that for a particular CNN, if you pass the image like this, for a particular CNN block you are having, there are actually hundreds of layers, and your input resolution will become, let's say this is my 416 by 416. And finally you are getting only 7 by 7 feature map. So your original input 416, it is reduced to 7 by 7. Now these 7 by 7 feature maps are very useful for detecting the objects as a higher level and identifying the class information. So basically it has more semantic information. Okay. So semantic information in the sense, which class does it belongs to? What is the object present in that particular image, right? Like that. Whereas it is lacking the spatial information. So for classification it is okay, but object detection we need the bounding box information also. Okay, wherever some object is there, we need the bounding box information also. So that getting that bounding box information, we need the spatial information, better spatial information compared to classification task. Initial layers, when you are passing, let's say you have a feature map like this, when you are passing the input image here, the initial layers will have better spatial features, or you can say low level features. That's what they call, right? In the initial layer of CNN, you will detect the edges, you will detect the corners, you will detect a particular curves, shapes, like that, right? So those are actually spatial features. But as you propagate through the network, and if you reach the higher level, right, what happens? You are only able to get the overall object shape like this. But the total edges or actual precise boundaries of those things, those kind of information is not actually kept intact as you propagate through this one. So for small objects detection, you need both the information. You can see that the resolution is more here, the resolution is less here. Okay, this can be 416 by 416, and this can be, let's say, 7 by 7. Okay, and the semantic information is actually increasing from this one to this one. So for object detection, we need both the information. Only one information is not good enough for identifying the objects, for smaller objects or for larger objects, for getting the precise boundary of the object, right? Bounding box. For these things, only having high level feature is not good enough. So we need low level features as well as high level features. So that is the main problem here. Now to solve that, you might have seen the SSD paper, single shot multi-box detection. They have done the predictions at different stages. Now instead of doing only on the last stage, let's suppose this is my last stage. Now from here it will go to detection head, where you actually predict the bounding boxes, all those. That's what it is doing here, right? Now instead of taking only the last layer, what if you take the features in between also? Okay, so this is only for representation purpose. These are kept side by side, but actually there can be possibility like, okay, this is my input 0th layer, considered as 0th layer, and this is my, let's say, 10th layer, this is my 50th layer, and this you can say 90th layer. Okay, there can be multiple layers in between also. Only for representation purpose, it is kept it as these are consecutive. But overall network can be 90 layer network, and the predictions are happening at 50th layer and then 90th layer. Like this, you can take samples predictions from the feature maps at different levels. Now what happens? Why do we need this? 90th layer has the highest semantic information. Now 50th layer has somewhat spatial information also. Spatial and semantic. Now if I take one more here, prediction here, at only 10th layer, then I have more spatial information here, right? So like this, if I make predictions at different levels of the feature maps, then I might be able to take care of those predictions, right? Bounding box predictions. This is the idea here. Now there is one issue with this idea. What is the issue? The issue is the predictions happening on this one and predictions happening on this one are independent. So here you are getting only semantic features. Here you are getting some semantic and some spatial features like that. Whereas the predictions are independent, whatever the proposals or bounding boxes you are predicting, those are independent in these layers. Now, even though you are making the predictions at somewhat slightly lower layers also, but where are you combining them, right? For every bounding box, let's say this is the person I want to detect. For every bounding box to detect, I need both semantic information as well as spatial information. But you are not combining these anywhere, right? You are only doing the predictions at different stages, hoping that this should solve the bounding box detection or any small objects detection problem like this. But when you don't combine these in an efficient way, you are still losing the information, and one is working independent of another, so it doesn't know still each other. So the predictions are not yet accurate. Now to solve this issue, FPN came. Now FPN, what it does is, it actually combines the high level feature map with the lower level feature maps to actually create a new set of feature maps. Have a look at this picture just for a couple of seconds to understand what it is doing, right? So this is my input, I am passing it here, and this is my backbone, okay, and my input all the way propagates till here. This is my, let's say, 90th layer. These are the highest feature maps which are having the highest semantic value. Now I need to combine the high level information with the low level informations like this across the stages. How do I do that? What should I do is, I will actually take a part of it, okay, and I will do one prediction on the highest level definitely, okay, and then what I will do is, I will do upscaling here. So the spatial resolution I will increase 2x. So this is actually upscaling. Now the feature map actually increased from, let's suppose that this is my 7 by 7. Okay. So this is my 7 by 7. Now let's say this is my 14 by 14. Now the feature map, when I do 2x, it becomes 14 by 14. And then the information from this one also is combined here through lateral connection. So this is actually combined through lateral connection. Okay. So this is what it does here. this is one high level feature map and then one low level feature map. You are actually combining both to create a new feature map here. Same way, here one more 2x happens, and then here let's say 28 by 28 it becomes. Now the equivalent 28 by 28 feature map, wherever it is available, that particular branch you will actually add it here. So what happens when you are going this way all the way, the resolutions are becoming half at each pooling stage, whereas when you are coming down, the resolutions are becoming 2x into 2. Okay, and then wherever you need the particular concatenation, you actually take the corresponding feature map size. Wherever 28 by 28 is there, you take the corresponding feature map from the backbone, you concatenate those features. It's not concatenation, it's an addition actually. So when you do this, you have better features coming up now, because you are combining the high level feature maps and low level feature maps and creating a new type of feature map like this. So these are actually new set of features. These are not the features from the backbone. These are actually new set of features which are generated here. Okay, so the predictions are happening on top of these features now. As these are the combinations of already the high level and low level, these predictions should actually give better bounding box information as well as the class information. That is the use of FPN. So far we have discussed about FPN, but it is not used in YoloV4. FPN is not used. As I was saying, FPN we need to understand just as a building block to understand the next module. In YoloV4, path aggregation network is used here, and path aggregation network is just an extension of FPN. You can see here till this particular block it is FPN. Okay, so this is still FPN. On top of FPN you add additional blocks. These are all the additional blocks you are adding on top of FPN. Okay, so that is why to understand this path aggregation network we need to understand the FPN. Why do we need to add another branch here? FPN seems to be working fine for the object detection, but why do we need these extra additional information? You can see how it looks like, right? Whatever the path aggregation network, it is just adding one more branch, one more bottom up path. There is already bottom up from the backbone, and then you are adding it a top down approach in the FPN, and then again one more bottom up is added in the path aggregation network. But why do we need this another branch here? Why should we add another branch? One simple reason is to shorten the information path. To shorten the information path. What do I mean by shorten the information path? Let us understand it clearly. Let us assign these names. Okay, let's suppose that this is my input image. Okay, and this is my feature map at 10. This is my feature map at let's say 40, and this is my feature map at let's say 90. Okay, as I was mentioning earlier, these are not any consecutive layers. There are so many layers in between like this. So what is my target here? I want the low level information, whatever is available in this particular F10, to be available at the stage of F90. I need to combine this F10 with F90. That is what my target is. Now for reaching from F10 to F90, I have roughly 80 layers. So all these layers along all this way, my original F10 feature map is being modified at every particular stage till reaching this F90. And I am getting this information only from F90. Okay, for reaching this F10 information to F90, I am actually taking around 80 layers. This is just an example. So depending on the network sizes, for bigger networks like ResNet 151 or ResNext, all these networks, these layers even increase. Actually, there can be hundreds of layers. So instead, what if we add one more path here? What happens when we add this path? Okay, we understood that it is taking more number of layers to combine these things. So the information loss is there when you are actually propagating this way. Even though you are actually merging like this, you might not be getting the actual spatial information at the lower levels, whatever is available. You might not be getting that. You are only getting that through the lateral connection. If we add one more path like this, now what happens? What does this green line indicates? This green line indicates that whatever the low feature map here available, okay, this is the low level feature map. This one, there is a path formed now because of this. Okay, so there is a path formed like this, all the way like this. Okay, this particular path reaching here, let's say it takes 100 layers, whereas this particular green path, it only takes hardly like 10 layers, less than 10 layers. So the same information in the backbone, it is taking 100 layers. Okay, if you keep FPN only, then there is no way a shorter path exists here. This cannot go like this, right? The flow is like this from top down, right? The flow is not from bottom up. It is only top down here. So this particular information, it cannot go like this. This is not possible, right? Now with this particular path, it can actually go like this. Okay, taking only smaller layers, small number of computations to reach from this stage to this stage. So this particular green path is actually the shortest path. Okay, this is actually shortest path. Why is it? Now the information is actually propagating this way, right? All these are forward connections, till here to here, here to here, all these are forward connections, right? So the information can move from this way to this way. So that's why it is a shortest path. With FPN, there is no such path. There is no such shortest path. Only via this path, it has to come down. Okay, it needs hundreds of layers. So this is the reason, just by adding one more branch like this from bottom up, we actually shorten the path. This is not only useful in the forward pass, this is useful in the backward pass also. Because in the forward pass, the features are aggregated in such a way like this. But at the same time, during backward pass also, the gradients flow will happen like this. Right? So this is also one reason. And adding this additional branch actually improved the accuracy. They have done the analysis on networks and they proved that the detection MAP got improved. These are the results. You can check this particular and this particular lines. Okay, because these are the same networks. ResNext 101, ResNext 101. On the same network, MAP is 37, whereas here it is 40. And with multi-scale training, it is 42. Okay, you can see everywhere it saw 2 to 3 MAP jump. Only difference is, instead of using FPN here, it has used path aggregation network. Okay, with the addition of this only one block, you can see that it has like 2 to 3 MAP jump, right? So that is the motivation for path aggregation network. Now there is one more modification in path aggregation network. Not only this particular branch, there is one more modification. We have seen that in the feature pyramid network, the predictions are happening at every stage. Okay, even though the features are merged properly like this, the predictions are still happening independently at every stage. And one more thing is, for predictions you usually have anchor boxes, or you can say proposals. So these are the boxes, preliminary boxes you will use, and later you will predict the offsets with respect to these boxes. Now these anchor proposals you will actually do at different scales, because to detect the larger objects you need small scale feature map. You can say that if you see this feature map, right, this particular feature map is actually used for detecting smaller objects, whereas this is used for detecting larger objects. Okay, that is how it is. So these anchors, whatever you are proposing also, these will have different scales. So we have seen this already in YoloV3 also, previous YoloV4. Usually the anchors are taken at 3 or 5 scales, and then each scale you actually take the features at different levels like this. Let's suppose that here only larger images, larger objects are possible. Let's suppose that. Now out of these 3 scales, now I have like 3 scales. Okay, now scale 1 is used here, scale 2 is used here, scale 3 is used here. Even though the predictions are happening on multiple branches, there is still no interconnection. They are actually fixing one particular scale to one particular feature map. Okay, scale 1 should happen on this feature map. Let's suppose this is feature map 1. Okay, you can say in P1, because usually you see in many papers the terminology used is P1, P2, P3 or like this, or you can say P4, P5, P6 like that. Okay, terminology. So this kind of correlation is there. Like, okay, P1 feature map, it should use for scale 1. P2 feature map, it should use for scale 2. P3 feature map, it should use for scale 3. This kind of correlation is there for predicting the boxes. Now with this one, there is an issue. There can be the case that even though the boxes are for scale 1, it might have some useful information even in P2 also, right? Why not to have these connections, right? So that is one issue here in FPN. That might be one reason the accuracy is lower also compared to PANet. Now in path aggregation network, what they are doing is they are actually combining them into a single unique feature map. So instead of doing the predictions on all the feature maps independently, we do adaptive feature pooling. So this is actually called feature pooling. Adaptive feature pooling is used actually to actually choose the best features for the predictions, because we don't know which are the best features for predicting any particular bounding box. The network should learn those things, right? So that's why actually this kind of pooling is happening from all the feature layers, because after doing this kind of pooling from all the feature layers, okay, this is what happens here, pooling. So after doing the pooling, then you are actually getting the best feature maps, best particular features for predicting that particular box. Now after applying this adaptive feature pooling, they have done an analysis on the relation between scales of proposals and feature levels. Now in adaptive pooling, irrespective of the scale, bigger boxes, smaller boxes, or even smaller boxes, irrespective of the scale, all the feature maps are available to them. Now they have done a backtracing of the analysis on taking a particular scale S1. Okay, for this particular scale there are like P1, P2, P3, P4. These are the levels of features. Which particular features it is taking, right? That kind of backtracing they have done. If you take S1, okay, scale S1, it took 10% of each features from this one. Okay, let's say 20% here, let's say 40% here, and 30% here. It might be taking the information from all the levels like this one, this one, this one, this one, like this, right? So that kind of backtracing they have done, taking each and every scale chosen along with the feature levels. If you check this is the graph looks like. These are actually proposals. So these are proposals, or you can say scales, proposal scales. Now blue is actually scale 1, orange is scale 2, like yellow is scale 4, like the different scales are there. And these are actually levels, feature levels. Okay, so these are feature levels. You can see that. Now let's say for example I want to take yellow color, yellow line. Okay, so if I want to take this yellow line, now yellow line is taking almost 0.05, almost 5% from level 1 features, and it is taking 25%, almost 23% from level 2 features. It is taking almost like 25% from level 3 features. Okay, and it is taking 40% from level 4 features. You can check like that. I will write down these numbers. Let's suppose that here 5% from level 1, okay, 25% from here, 25% from here, let's say 40% from here. Okay, on average if you take plus or minus 2, 3 like that, overall you should get actually 100%. So you can see this particular yellow scale, let's suppose this yellow is actually scale 1. Okay, so this might be looking for only larger objects. If you consider that this is looking for larger objects. Now larger objects, if you consider like this, okay, so this is level 1, this side you can see this is level 1, level 2, level 3, level 4. Usually bigger objects you can detect from these feature maps. This is actually having more information regarding the bigger objects. So from this intuition we can understand that, okay, level 4 feature, okay, this is L1, level 2, level 3 and level 4. As yellow is actually looking for larger objects, it has taken most of the information from, like 40% of the information from level 1, and level 2 and 3 it took 25% of the information, and it took around like 5 to 10% information from level 1. So this is the information distribution for this particular yellow line like this. So they have observed that even though it is actually fixed to a particular scale, it requires information from all the feature levels. So that is where fixing the feature level to a particular scale is not valid actually. So they have adopted this kind of feature pooling so that you take the important features from all the layers. So if you check this particular bounding box, this is the same box. Okay, so let's say B1, this is the box you are having. They have actually took features from different levels for the same box, same proposal, and then out of these features you take the best features by doing some analysis. How they are taking the best features we will see, but they are only taking the features from all the levels, only important features which are good for identifying this particular box. How do they do that selective pooling or adaptive pooling? We will see that. So you can see here this particular B1 bounding box, it is adapted here, it is used here, it is used here, and it is used here. On all the feature levels, the bounding box B1 or proposal P1, whatever you consider, that particular scale, the features are extracted using ROA align. ROA align makes it a fixed size feature map. So all these are fixed size. Even though they are coming from different feature map levels, the output is fixed size. Okay, ROA align is actually used in mask or CNN, so it's a different topic altogether. You can go through that. It actually creates a grid kind of thing. Okay, if this is my feature map, you actually create this kind of grid and you take one portion, you take the maximum out of it. You take one portion, you take the maximum out of it, like this. Okay, it is similar to ROA pooling, but it is slightly different. It actually does interpolation and all that stuff. So you can go through the mask or CNN paper for understanding this. So the end output is the feature maps corresponding to this particular block, okay, are taken across different levels, and all these are the outputs which are fixed size. Now out of these are features still from different levels. Now I need to combine them. So how should I combine them? Let's suppose I want to use a fully connected network. Now all I do is I will flatten this one into a single vector. So these are one-dimensional vectors, let's suppose. Now what I will do is I will take element wise sum or maximum or sum. Element wise you take the maximum element, or you sum all of them together and take a single value. So let's suppose this is my first block. Okay, this is my first element from all these things. Now this particular first element I will take from all of these blocks. All of these I will take sum or maximum of those to get a single vector like this. And similarly, if you are not flattening and doing like this also, if you are using only fully convolutional networks also, even from this fixed size also, actually you take this particular portion. Let's suppose that you are only taking this portion here. Now this portion, you take the same portion here from all these things, you take the maximum of those individual value and then you pass it through to get a single block like this. Okay, so this is how the aggregation is happening. So the features are taken at different levels, yes, but then once the features are extracted, they are actually taking the maximum element or sum of the elements. So it is element wise operation they are doing across all these levels to take only the prominent features, because when you take the maximum, right, only the prominent features will come here. So that is what it is used later for bounding box and class predictions. Okay, so this is how the path aggregation network works, and it is used in YoloV4. Now the path aggregation network is not as it is used in YoloV4. They have made a slight modification. In path aggregation network, or in case of FPN also, when you are doing this lateral connections, adding this addition is happening, whereas in case of YoloV4 they have replaced the addition with concatenation. Okay, just one simple operation. So you can see in detail here. Okay, so this is the original path aggregation network. When you are doing this, right, so like this, when you are combining these two, here actually to get this particular value you are adding this one, whereas here concatenation. That's why you have a single feature map here, whereas you have two blocks here because of the concatenation. Same level, this particular thing downscaling will come like this, whereas this is coming here again an additional block. So this is the modified path aggregation network. It is using concatenation here, whereas this is using addition and this is using concatenation. This is one difference they have made. So this is only to combine more features here at the end. So you have double number of features here, right? And after that you are anyway using ROA align and fusion of all of those things, like maximum element, taking the maximum element. That is what fusion is. Okay, so this is how the path aggregation network works actually. Then we will see spatial pyramid pooling. Along with path aggregation network, spatial pyramid pooling is also used in YoloV4. This is again another paper altogether. All of the techniques whatever we have discussed so far, these are all separate research papers, and I have tried my best to make you understand them. Okay, these might not be in detail information I am providing here, but these are good enough to understand the intuition behind them and basic working of that particular module. Okay, if you want to go detail into this, you can go through the papers. I have provided the links to all these papers in the description. So let's come back to SPP. Spatial pyramid pooling is added on top of the backbone CSP DarkNet. Now this is actually used to get more significant context features. To get better contextual features, actually you use spatial pyramid pooling. So this also helps in detecting the objects at different scales. If you check this is one particular scale, this is one particular scale, this is one particular scale, like this. So this also helps in detecting the objects at multiple scales. Now where is it used in the YOLO? After the last convolution layer, okay, in the CSP DarkNet, after the last layer, they have actually removed one of the pooling layer, and then that particular pooling layer is replaced with spatial pyramid pooling layer. It is a kind of pooling layer, but it's not direct pooling like a 2x2 max pool or like that. Okay, you actually take a particular feature and you take different levels of features from the pooling. Okay, it's not a single pooling. So the main operation is, this is similar to ROI pooling. Okay, and this is almost the similar concept which is used in PAN also for aggregating those features from different levels. Whatever I was saying, right? Like these features, ROI align. Okay, these features taking, I am saying it is giving fixed size. How fixed size is coming? We will see here. This is giving the fixed size again, fixed length representation. How? Now I decided that this is 4x4 grid. Okay, now I will take 4x4 grid here. Let's suppose I want to take this grid. Now in this particular grid I have, let's say 10x10 pixel values. Now out of this 10x10 I will only take one value, maximum value, right? Now this particular grid will have that maximum value. Similarly, it has you can do multiple things like this at different resolutions, like different grid values. Like here, let's say it is 2x2 grid, 4x4 grid, and 1x1 grid. Okay, 1x1 grid means this total you will get a single grid value, and out of all of this you take the maximum value. So it will give a single value here. You can see it is a single value. 2x2 grid you have 4 values. 4x4 you have 16 values. Okay, so like this, depending on your grid number, your output value will come. So as you are fixing the grid numbers, your output will be always fixed like this. Okay, so this is what ROI pooling is, and the same concept is used here. Only thing is with the different grid levels. Okay, so instead of doing a simple pooling, you take the grid values of different levels and you take the features of different levels. Now it is like taking the maximum value of this total grid. You will take the highest significant feature available in this total block, whereas you divide into multiple blocks, multiple grids, and you take local features, right? So kind of you are getting pyramid pooling, right? So at different levels, okay, this is the highest pyramid, this is the second highest, this is the lowest pyramid, right? So this kind of pyramid pooling you are doing by using the grids here. In YOLO, how it is used, you can see like this. In YOLO, let's suppose that this is 1x1 grid, this is 3x3 grid, this is let's say 5x5 grid, like this. Let's say 7x7 grid is there, one more. Like this you do multiple grids on the feature maps. Then you will get a fixed size feature maps. Okay, so let's say the channels are 512. This F map, what are the feature map size, this is fixed actually. And then you concatenate all of them together before passing to the next layers. So this is how the SPP is used in the YOLO. Now let us see the attention module. Okay, so there is another block which is used in YoloV4, which is SAM, Spatial Attention Module. So to understand that spatial attention module, we need to understand what is an attention module first of all. Okay, if you see this is my input image passing through a CNN, which is a backbone, let's suppose, and then you are getting a feature map like this. These are some features. Okay, these dots, yellow dots or red dots represent important features. Okay, and the blue one is not much important. So these are the features you are getting. This is actually an interesting paper. I got the figures from a paper called SCR-Det. I will provide the link in the description. This is actually on DOTA dataset. It's like satellite images. This is actually detecting the buildings, swimming pools, aeroplanes, all these things from the satellite images. So these satellite images, let's suppose this is just an example. In that paper, I got these figures. These are very intuitive for understanding the attention module. Now, if you see this, these are the objects, it's fine. But you can see this is actually unnecessary features, unnecessary hotspot I am getting, right? This is all extra feature. I don't need this. Attention is, in simple terms, getting the most important thing. That's it. Discarding others. Okay, it's kind of giving weightage. So giving weightage to more important features and reducing the weightage to less important features. That is what attention is. Okay, in simple terms here, if you see this is all noise, white spots, all these are, which are not required for our object detection here, detecting these objects. So all these are ignored here after passing through attention block. And what are the important features which are useful for our detections like this? These are the boxes here. You can see these are the boxes. For detecting these are the important features. So only these are kept. All the other things which are these blurry additional things along the boundaries and this one in the background, all these are eliminated through the attention block. So this is attention block. Now what is this attention block? Attention block are actually two types. One is channel attention. Another one is spatial attention or pixel attention. Whatever we are discussing, we need to see in YoloV4 is spatial attention module. So you have some set of input features. You do some kind of operations here in the attention block and then you multiply that with the original features. Whatever the original passing it here, you are actually multiplying them and then you will get a refined feature like this. This is how the attention block looks like. Now we will see the spatial attention. So this spatial attention, let's suppose that this is my input feature map I am passing and after doing some kind of processing, I will get this kind of features. Now I will multiply that with the original to get the better features like this. Okay, so what we are doing is max pooling and average pooling. You can see this is actually max pooling and this is average pooling. These are the feature maps. This is actually along the channels. Along the channel dimension, if you do, for every pixel value you will get the maximum value. For every pixel value you will get the average value along that particular channel like this. Now these are only 1 and this is 1. Like you can say like this is by 10 by 10, right? So 10 by 10 by 2. So this is the dimension of this particular block. And then you perform convolution and you will get this particular block. Okay, same 10 by 10 block you will get. And then you apply sigmoid here to get between 0 and 1. Okay, you can see that this is, let's say, 10 by 10 feature map. For every pixel here, for every pixel I am getting 0 to 1 in between weightage, like 0.9, 0.8. Let's say for this one I am getting 0.7. Okay, for this particular red dot I am getting 0.9. Okay, so these red dots indicates the higher values in the range of greater than 0.7, 0.8, 0.9 like this, whereas this blue color indicates 0, 0.001. Okay, 0.0002 or something like that. Whereas when you have these little shades of yellow, then you have something like 0.5 or 0.6. So you get the high level idea, right? So basically this is sigmoid output. Every value will be in between 0 and 1. So it's kind of weightage. Now you are multiplying this with your original feature map. Now what happens? Whatever the zeros are there here, this particular all the blue region behind it, right? All those, when you multiply with these some values here, some values will be there here. When you multiply with 0 point something, all these will get nullified. And at the same time, when you have 0.9, 0.7, all these things, those things will get boosted. So your feature map, whatever it looks like this, it gets converted into this using a weighting factor. So this sigmoid output, whatever we are getting, these are actually weights, kind of weights you are getting. Okay, so in the spatial attention, what exactly we are doing? We are actually doing max pooling or average pooling, and then you are performing the convolution and then taking the sigmoid. So this is a learned path actually, right? And then you are multiplying this here to get the final feature map. This is the spatial attention module. Now this spatial attention module, instead of using maximum pooling and average pooling, in YoloV4 they have modified it to use a convolution block. This total thing is replaced with a single convolution block. That is what it is used here. You can see this. This is the original spatial attention mechanism, and this is the modified spatial attention used in YoloV4. Instead of doing the pooling operation, what they thought is pooling operation does lose some information because it only takes the maximum value or it takes the average value. So instead, what if we learn those features also through the convolution? Which features to take? Instead of taking the maximum feature directly, right? Which one to take? You learn through convolution. Then you have a block like this, and then you perform the sigmoid. So you will get the weightage here, weights. You then multiply those weights with the original. Okay. Then you will get the refined feature maps. These are refined maps. This is actually kind of boosting your important information and then suppressing the non-important information. That is what the sigmoid does, right? Sigmoid actually curve is like this. So that is what it is being used in the spatial attention module. So these are the major architectural details from the YoloV4. We have discussed about backbone and discussed about neck part, which is a combination of SPP and PANet and SAM. And then detection head is remaining, but detection head is exactly same as YoloV3 detection head. The bounding box prediction, offset calculations or target calculations, objectness score and class predictions, all of those are happening exactly same in the way it is happening in YoloV3. So we are not going in detail into the head part in the YoloV4. In fact, we have already discussed some of the modules in bag of specials. Okay, all these are architecture changes. We have seen the Mish activation function, which is being used in backbone part. I did not go detail into Mish activation because it's already discussed in our previous videos of activation function series. You can go through that to understand Mish activation. We saw cross-stage partial networks, how it is used in the backbone, CSP DenseNet, CSP DarkNet. And then we did not see this, but it is actually very light module. It is actually multi-input weighted residual connections. So we have these interconnections in the DarkNet, right? From one block to another block, there are interconnections in the DenseNet blocks. Now those interconnections, instead of directly connecting like this, what if we add a weight values like W1, W2, W3 like this weighted values? And what if you learn those weights like this, right? So these residual connections, instead of directly adding the residual connections, you add the weightage to that. So that's a very simple concept. We saw SPP block and we saw SAM spatial attention and we saw path aggregation network, right? So most of the bag of specials we have covered in this video. Bag of specials, as I mentioned previously also, these are major architectural changes which are very useful for increase in the accuracy, major boost in accuracy it will give with slight increase in the inference speed. So most of the things are done. DIO NMS we will discuss it later, actually in the next video. So in the next video we will discuss about the remaining bag of freebies and bag of specials. Whatever the remaining topics are there, all these things we will see in detail in the next video. Thank you.